this series of lectures on quantum mechanics, the last topic is the hydrogen atom problem, and in part 2 today I shall discuss the 1s orbital. This is a very important orbital for this hydrogen atom. Orbital, let me first define what is meant by orbital. Orbital is the contour or some region in three-dimensional space where the probability of finding this electron is maximum. It is in contrast with the orbit, which is two-dimensional in nature. The orbital is designated by this azimuthal quantum number L, and when L equal to 1, L equal to 2, L equal to 3, L equal to 4, etc. It is also indicated by the letters. Say L equal to 1 means S orbital, L equal to 2 means P orbital, and L equal to 3, L equal to 1 equal to P orbitals, L equal to 2 means D orbital, L equal to 3 means F orbitals. S, P, D, F, they are originating from this spectroscopic term in atomic spectra. S means it is the sharp series, S coming from the sharp series, P from the principal series, D from the diffuse series, F from the fundamental series, etc. The orbital is designated by the wave function, and this wave function psi NLM r theta phi. NLM, these are the quantum numbers which define this psi function, wave function, and r theta phi, the variables on which this psi depend. So psi NLM r theta phi is a product of three functions. R function, R equal R NL defines this R function, radial function, and it depends on R, and LM defines this P function and it depends on theta, and M quantum number defines these F functions, it depends on phi. For this 1s orbital, N equal to 1, this is the lowest energy wave functions for this lowest energy state, and so N equal to 1. When N equal to 1, L equal to 0 and M also equal to 0. When this L and M both are 0, so this psi 1s is represented by psi 100 also. Since L and M are 0, so the P function and F function do not contribute to building of this 1s orbital. Only the R radial function constitute the orbital expressions of this 1s orbital, and this function RNLR is obtained from this radial part of the Schrodinger equations of this hydrogen atom. And the radial part we have already discussed, 1 by r square d by dr, r square dr by dr, plus 2 mu r square by h cross square, e plus p square by r, and minus L into L plus 1 into r equal to 0. L is the azimuthal quantum number. So the analytical expressions of psi 1s coming from this radial function, it is a into e power minus r by a naught. R is the radial distance, and as the distance of this nucleus distance of this electron from this nucleus increases, the psi 1s value also decreases, and a naught is the Bohr's first orbital radius, and it is equal to h cross square by mu e square. So the A is normal, and A is normalization constant and obtained from the normalization condition, and the normalization condition integration or space modulus square of psi 1s deta equal to 1. Deta equal to r square dr sin theta d theta d phi, and putting this psi 1s value here, a square will go outside of the integration 0 to infinity, and e to the power minus 2r by a naught psi square, psi 1s square, so 2r by a naught r square dr coming from this deta, and it is the sin theta d theta, and 0 to pi integration limit, and here 0 to 2 pi integration limit, and d phi equal to 0. And if we do the integration and put the limit, then a will be coming pi a naught cube to the power whole to the power minus half. And so the normalized 1s orbital is given by pi a naught cube whole to the power minus half into the power minus r by a naught. And whenever the energy value, eigen energy value of 1s orbital we like to determine, it could also be determined from the solutions of this radial part of this Schrödinger equation of this hydrogen atom. This is the lowest energy of this hydrogen atom. But it could also be obtained by using this eigenvalue equation. H cap psi 1s equal to E psi 1s. And H cap is the Hamiltonian operator, and this is equal to minus H cross square by 2 mu and del square. Del square is the Laplacian operator plus V cap. V cap is the volume. V cap is the operator of this potential energy. So this one equal to minus H cross square by 2 mu, and instead of Laplacian operator we can write here this one. This theta and phi part is dropped as this function does not depend on theta and phi, and this is the operator of potential energy minus E square by r. So H cap psi 1s equal to minus H cross square by 2 mu 1 by r square d by dr r square d psi 1s by dr minus E square by r psi 1s. And putting here this value here coming, and in this case 1 by r square d by dr, and this r square, and instead of 1s we write a into e to the power minus r by a naught to dr, and this value set, and equal to minus h cross square by 2 mu 1 by r square, and the differentiation minus 1 by a naught into d by dr, and there r square a into e to the minus r by a naught, and this value remains same. And this one equal to minus h cross square by 2 mu and 1 by r square, this value also remains the same, and this is the product of two variables, and whenever differentiating with respect to r, this r square remains intact, and this differentiation minus 1 by a naught into e to the power a into e to the power minus r by a naught plus twice r square and twice r, and this differentiation twice r a into this value, and this one remains the same. Whenever multiplying this one minus h cross square by 2 mu and 1 by a naught square, this one and this one, minus 1 plus a naught square, and r square cancels, and this one only 1 by a naught square, and a into e to the power minus r by a naught, this is this psi 1s, this one is also psi 1s, so this one also psi 1s, so psi 1s have been taken common. So this value will be equal to 2 by r a naught, this one plus becomes minus, and minus e square by r, minus e square by r, and psi 1 is a common. So whenever it is multiplying, again minus h cross square by 2 mu, this equal to, and putting these values a naught equal to h cross square by mu e square, the whole square, and here also a naught is replaced by h cross square by mu e square minus this one given straight. And this value actually 1 mu cancels, so mu 1 mu remains up in the numerator, and e to the power 4 also there, and here 2 here, and 1 h cross square plus this value h cross square cancels, and mu cancels, and so it will be e square by r minus e square by r outside. This value and this value, these two values are cancelled, and so it becomes minus mu e to the power 4 divided by 2h cross square into psi s. So energy value of this 1s orbital equal to minus mu e to the power 4 by 2h cross square equal to, in terms of h, minus 2 pi square mu e to the power 4 by a square. So this value is found to be negative, means electron is bound within the hydrogen atom. So energy will be required to remove this electron from this hydrogen atom, and hydrogen atom here remains in one s orbital, means a ground state, isolated and in gaseous state. So energy required to remove this electron from such an atom is called the ionization potential. Ionization potential equal to 2 pi square mu e to the power 4 by h square. Whenever we are putting this value, this pi, this one, and mu 9.1 into 10 minus 31 kg, and E 1.6 into 10 minus 19 coulomb into 2 to the power 4, and divided by 6.626 and 10 to the power minus 34 joule second whole square. So whenever calculating this numerical value, it is found to be 21.69 into 10 to the power minus 19 joule. Since it is a very small value, so it is usual practice to express this ionization potential in terms of this electron volt. 1 electron volt equal to 1.6 into 10 to the power minus 19 joule. So this amount equal to 13.56 electron volt. Means this amount of energy is required to remove this electron from this hydrogen atom, isolated gaseous state in ground state. And psi 1s is also found to be independent of r. With the motions of this electron, actually r is changing, so kinetic energy, potential energy both are changing, but this total energy remains a fixed constant, and this hydrogen atom in this orbital remains for an indefinite period of time that could be supported from this Heisenberg uncertainty principle. Del T equal to half h cross by del E, and here E equal to constant, so del E equal to 0. So this delta T equal to infinity means duration lifetime for this electron for the hydrogen atom to remain in this state is for an infinite period of time. Energy value of this 1s orbital, or it is taken as the ground state energy or 0 point energy of this hydrogen atom, is given as minus mu e to the power 4 by 2h cross square. Now other two terms, I also like to calculate this angular momentum, which is L equal to the power L into L plus 1 h cross, and but L equal to 0, and so this angular momentum also equal to 0. Z component of angular momentum equal to mh cross, and m, since m equal to 0, so this Lz value also equal to 0. So this shape of 1s orbital, since angular momentum and z component angular momentum both are equal to 0, so this shape of this orbital is a sphere, or spherical. This can also be obtained by taking this graphical plot, and shapes of these orbitals could be done by two methods, method number 1 and method number 2. Method number is to draw the function against r, and the second one to draw the contour contour surface of this equal probability density. So this is the first one, method 1, psi 1s versus whenever r is plotted. R is plotted, and this one gives you the when psi 1s equal to this value and a equal to this value, and when r equal to 0, this psi 1s is maximum and this maximum value is equal to a. Means near this nucleus, this function having the maximum value. As this r is increasing, psi s1 also decreasing exponentially. And when r tends to infinity, this psi 1s tends to 0. But practically psi 1 is equal to 0 at r equal to 2a0. Means if we consider a spherical set, if we consider a sphere of a definite radius, then at each point on the surface of this sphere will have the equal value of the psi 1s. This concludes that the psi 1s orbital is having the spherically symmetrical in shape. And psi 1s square versus r plot, again psi 1s square equal to a square into e to the power minus 2r by a naught. And again this when r equal to 0, this probability density is found to be maximum, and this is equal to a square. This is equal to a square. So when r equal to 0, psi 1s square equal to a square. This is the maximum value. As r increases, psi 1s square decreases very rapidly, exponentially decreases, but more rapidly than 1s versus r. When r tends to infinity, psi 1s square equal to 0. But practically psi 1s square equal to 0 at r equal to 2a0. It means that near the nucleus when r is about to 0, the probability density or probability of finding this electron is maximum, and it is fading away or decreasing very rapidly with this increase of r. So I can do an analogy. I can give an interesting point. So suppose this is the nucleus, and around this nucleus, given the dotted, and near the nucleus, the probability density is maximum, and as this r is increasing, the probability density is decreasing very rapidly, and when r equal to 2a0, this probability density almost tends to 0. So suppose if I sit on this nucleus and watch this electron cloud density, just like fog density, then around me the fog density is maximum. As I am looking the further away from this nucleus, means from me, this fog density is decreasing very rapidly, and when this distance from this nucleus is equal to 2a0, the fog density almost will vanish. Now next one, another thing is that radial distribution function or radial probability density distribution function PR. This is very important concept. This is a very important concept to get more knowledge about this 1s orbital. This is the volume of the, let us consider a spherical cell. Let us consider a spherical cell of radius r and thickness dr. And the volume of this spherical cell is equal to 4 pi r square dr. 4 pi r square the surface area of this sphere, and dr the thickness, and the multiplication of this 2 is the volume. And when this volume is multiplied by this probability density, we get the probability of finding this electron within this spherical cell of radius r and thickness dr. And so this is denoted by PR dr. PR dr equal to 4 pi r square dr into psi 1 square means a square into e to the power minus twice r by a naught. This is these two keeping constant here, and r square this one. So PR actually a dash is this term within the bracket is a dash r square e to the power minus 2r by a naught. So this PR defines as the probability of finding the electron within the spherical shell of radius r and thickness unit. And when PR is plotted against r, we are having this such type of plot. When r equal to 0, this PR equal to 0. So as r increases, this term r increases means r square increases, this value of PR, and this term decreases this value of PR. This is the Gaussian distribution function. So when the value of r is low, this term is dominating, and so PR increases with this increase of r. And then when r is high, then this exponential, this one is non-exponential, this one is exponential. Exponential term dominates, and the value of this value will decrease this value of PR. So it is decreasing. And when r equal to infinity, this PR again tends to 0. So actually the curve of PR versus R starts from origin and increasing and attains the maximum value and then decreasing to asymptotic value. So in comparison to this one, if we plot the psi 1 square, then what the probability density is found to be very high, maximum when r equal to 0, but this but the probability of finding this electron within this shell near to nucleus is 0. So this becomes a very interesting point to see. For the illustration, I can take one example. Suppose we are having these rings. Of equal length and increasing the radius, and they are composed of materials of decreasing the density with this increase of r. Then this ring, which is just at the center, very smallest one ring, mass of that ring equal to dV into rho. Rho is very high value, but the dV is small. But if we consider the very large radius ring, then volume is very high, but the density again is very small. So in between the two, there must be one ring just having the intermediate radius whose mass will be the maximum value. It is similar like that. Rho here the mass density, here the rho is the probability density, and dV the volume, and this is the volume of the cell. So if you try to find out the value of R max, then dPr by dr equal to 0. This is the conditions for this extrema. So whenever we are differentiating with respect to R, a dash is constant, and p by dr r square, and this value here equal to 0. So when we are differentiating these product of two variables, r square twice r, and this value remains same, plus here r square remains same, and this one differentiating with respect to r e to the power minus 2r by a naught and minus 2 by a naught, and taking common a dash square 2r e to the power minus 2r by a naught, taking common 1 minus r by a naught equal to 0. So these three possibilities are there: r equal to 0, or e to the power minus 2r by a naught equal to 0, or r equal to, when this one equal to 0, r equal to infinity. So r equal to 0, r equal to infinity, these two are the minimal point of this curve. So another point 1 minus r by a naught equal to 0, and this will correspond to this maximum value, and so r max equal to a naught. So this result, what does it mean? If we consider a spherical shell of radius a naught, the probability of unit thickness, there will be maximum probability or finding this probability maximum. And this is consistent with this Bohr's radius, and Bohr states that in case of 1s or ground state energy, in this case electron is revolving around the nucleus in a circular orbit of this radius a naught. But there is a difference in concept, and in this case of quantum mechanics, it is the probability of this electron to be found, maximum probability for this electron to be found within this spherical shell of this radius of a naught. But Bohr's concept gives this certainty for this electron to be found out. Now I shall calculate the average value of R. This expectation value or average value of R is given by this way according to the Dirac's notation, when psi 1s is normalized. So this will give you pi a naught q to the power whole to the power minus half e to the power minus r by a naught, and r multiplier, and this function psi 1s and d tau equal to r square d r sin theta d theta d phi. So integrating this one, pi a naught, this value minus half becomes minus 1, and this go outside of the integration, and this one it will be minus 2r minus 2r by a naught into r square, and here r cube dr, and 0 to pi sin theta d theta, and d phi 0 to 2 pi. And whenever this integration is done, this integration is done by using this gamma function, and so the total this expectation value of r is equal to 1.5 a naught. This value conclusively proves that there will be a finite chance or definite chance for this electron to be found beyond the distance a naught. Means a naught is the radius of the spherical shell at which this electron probability is found to be maximum, but beyond this a naught radius, there is a finite chance for the electron to be found. The average value of x or expectation value of x is also obtained by this way when psi 1s is normalized. And putting this value here, and x equal to r sin theta cos phi, and psi 1s equal to and d tau. So psi this two whenever multiplied, this one occurs minus 1 whole to the power minus 1, and this value is e to the power minus twice r by a naught and r square, and here 1 r cube here, and this is sin square theta d theta 0 to pi, and 0 to 2 pi cos phi d phi. But cos phi d phi, this integration limit 0 to 2 pi equal to sin phi 0 to 2 pi 0. So x equal to, so this term 0 means expectation value of x equal to 0. So this also proves that the 1s or 1s square both are spherically symmetrical. So the chances for this electron to be found at plus x and minus x from this nucleus is equal, leading to the average value of position is equal to 0.
This is all about the 1s orbital, and next day, part 3, I shall discuss these 2s atomic orbitals, and 2s atomic orbital is a little bit more complicated than 1s orbital. And thanks to you all who are watching this video, and if you like this video, then you please subscribe.